So this is the Beal.
Okay, cool. The Beal function. All right, let's, can you just, are you only sharing Excel, or could you bring up an image of the Beal function so we can visualize what's going on here?
This is the
Okay.
previous iterations.
Great. Okay, so from, let's see, we're expecting a minimum.
At 3 and 0.5.
Okay, at 3 and 0.5. Okay, and what are you initializing to?
My initial guess
Yeah.
is -2, -2. So the same initial guess that we just used.
Okay, so you're initializing down in the bottom left corner. And what we're hoping is that it finds the solution at 3 and 0.5. Is that right?
Mhm.
Okay, great. All right, so let's go back over to your plot now. So you're initializing at -2, -2. All right. And which one is which? The blue and the orange.
I'll put the legend there.
Okay, so blue is optics. Wow, optics goes all over the place, huh?
That's where I was kind of confused at the results. I wasn't sure. And they both arrived at the correct answer, but I was unsure if I maybe did something incorrect.
Yeah, I'm not sure that you've done anything incorrect. So where'd you get the output from optics? Is that from the text file that it creates?
Yes.
Okay,
And
let's look at that for a second.
Right. I copied it over here.
Okay. Okay, this is fantastic. Okay, this is so, you know, I said I was going to come back to the first 3 columns in this output file, and this is a perfect example of what's going on here. So so notice that that optics is jumping all over the place, right? So if you come back there,
copy and bring this over so we can.
Okay, great. Yeah, let's can you enlarge your plot there just a little bit? Yeah, just drag it down so we can see it a little bit better. Okay, so it's kind of jumping all over the place, right? So we started at -2, -2, both of them initialized right there, and then optics moves up from there and over, and anyway, optics really bounces around in this design space a bit. Part of the reason for that is because at any point in the design space, now optics is blue, right?
Let me bring this over.
And SciPy is orange.
Yes.
Okay. Can you go back over to your other tab for a second?
Or just so you can see everything here.
Well, no, I'd like to go to your optics versus SciPy and just click on that the blue chart there. Yeah, okay. I just wanted to double check on that. And then the orange, if you click on the orange stuff, it's coming up with SciPy. Okay. All right, let's go back over to the other tab now. Okay, so remember that at each subsequent point, now optics, what you're not showing here is the line searches, right? These are actually the iterations. So that the file that comes out of this only shows you the next iteration, and it took 30 iterations to get to the final solution. But it's not showing the line search data, right? So each of the blue points on here is a different iteration, although there was a line search basically in the direction between each of these blue points. Does that make sense? And that line search included 8 or 16 or 64, you know, some number of points along that line in order to find the minimum in that direction. So what happens is that this design space is rather complex. It's certainly not quadratic, right? And we talked about how BFGS and these types of design spaces are really great for quadratic, but this is the Beal function. You can look up the equation for this. This is not a quadratic design space, okay? Great, yeah, there's the function right there. Okay, so what's gonna happen is as optics is progressing, it's assembling what we call the Hessian, right? So it's estimating from the first derivatives at two points, it can estimate the Hessian in that region, right? Well, it turns, and then it's using that Hessian to make a decision about where to move to next. And so if we go now over to the iteration column, so we've got A, B, and C, we've got an iteration in column A, and then we've got inner and outer iterations, okay? So the very first one, we call this iteration 0. This is our initial guess at -2, right? So that's the row 2 there. And then the next one, iteration number 1, is an inner iteration. And basically it goes to that next point. It computes so it now knows the gradient at 2 locations, your initial guess and the next point. It computes the Hessian, and it says, based off of this Hessian, there is no way now to go downhill. We have reached the minimum. And so at that point, actually, optics says, I've reached the bottom, because it's using not only the local gradient, but also the Hessian to estimate whether or not it's at a minimum. And so, so what optics then does is it says, okay, I'm going to erase the Hessian. I'm going to forget that I know anything about the second derivative, and I'm going to recompute. I'm going to start over from scratch in a steepest descent. Remember, the first step is always steepest descent, and then the next step has enough information now to build a Hessian. So so that's iteration 2. Then says, okay, this is now an outer iteration. I'm going to basically, every time it increments the outer iteration, what it's doing is erasing the Hessian, everything that it knows about the history of how it got there, you know, the history of those gradients that have been building this Hessian. So again, it goes back to steepest descent and says, oh, I can actually move downhill using steepest descent. And so it goes back into inner iterations again. And you can see it only does one more iteration. Based off of that Hessian, it says, again, I've hit a minimum. And so I'm going to go to another outer iteration, erase the Hessian, and start with steepest descent again. So
also it's helpful to see where you can see that, like, it has its alpha, what we talked about. And then when we get closer, it says that the alpha was too large, and it reduces alpha, and then it recalculates it. So then it does steps with reduced alpha, if that's kind of what, okay.
Yeah, as it gets closer to the optimum, it has to reduce the step size in order to capture the minimum. Alpha is basically how big of a step size it's taking, and it's got to reduce that as it gets closer and closer to the optimum. You can see that the blue points converge, you know, as you get closer to the optimum, the steps are smaller and smaller. And so the distance that it wants to take for that line search is smaller and smaller in order to capture a minimum in there. Okay, so anyway, this is the difference between an outer and an inner iteration. Every time it increments the outer, what it's doing is erasing its memory about the Hessian, and it's starting again at steepest descent. You can see that it has to do that 10 times in this design space. And that's because this design space is very nonlinear. Not only nonlinear, it's not quadratic. It's very much not quadratic. And so you can see that the Hessian, as it was computing the Hessian as it moved around in here, and these gradients, it got kind of bounced around in this design space because of how uneven or I don't know, nonlinear this design space is. But eventually,
I didn't put the correct bounds on the design space. For the
that's
function.
okay.
Okay.
Yeah, you're okay. It's not really necessary for this. So, but you can see that, you know, if we were to fit a quadratic to different regions in this design space, it would look differently. There are local valleys and things that are not really global minima. They're these little canyons and things, but there is really only one local or global minimum here, and everything points down to that, but it points down in kind of a complex way. And so it bounced around within here trying to find that. Now, as it got closer to the solution, you can see on line 26 over here, on the 10th outer iteration, it actually ran 6 inner iterations. And that is a sign that the Hessian now was didn't need to be erased as quickly, right? So it could still use information from the past. It was still marching downhill, even with that that Hessian that it was continuing to build. So for 6 iterations, it continued to build this Hessian that wasn't causing an issue. And by the time it got to the bottom of that one, it said, okay, I actually have reached the final point here. So anyway, that maybe what I'm explaining is a little bit complicated. And if you actually dug into coding this up yourself, I think it would be very clear what's happening here. But basically, every once in a while, it has to erase the Hessian because that information about second derivatives is not true at every point in this design space. And so it has to erase that information, that previous information every once in a while to kind of clear its mind, do steepest descent again, start over building a new Hessian for the new region that it's in. And it had to do that several times. It had to do it 10 times in this design space.
Where did you see that it has to do that 10 times? Where's that? Oh, right.
Outer iterations. Yep. Every outer iteration is a new time that it's erasing its information about the Hessian.
Okay. Got it.
And then it holds that information or it continues to build that Hessian according to the BFGS update within one of those outer iterations. And you see that very last one, it continued to add to that 6 times, that information about the Hessian. Okay, great. Kyler, thank you. Any other questions or comments on what's happened here?
I don't think so. I just think it's interesting that it kind of goes to it almost looks like it goes up to a corner, then another corner, then another, like the upper third quadrant, and then it finally settles just to kind of test each location. But I think that's everything. I think it is just really interesting to see how they solve them differently.
Yeah, again, you can see the orange one gets there really, rather quickly, perhaps compared to the.
It actually takes significantly more.
Oh, does it?
Mm-hmm.
Well, we have to remember what you're showing here for SciPy is every single function call. And what you're showing for optics is only the iterations. That the optics had to make a whole lot more function calls.
20 iterations for SciPy.
Yeah, SciPy is showing every single function call, and 20 iterations. Optics took 30 iterations, and we don't really know how many function calls optics took. We'd have to record it the same way we did with SciPy in order to figure out exactly how many function calls optics required.
Okay.
So it's not apples to apples for the numbers, the length of those columns here. Does that make sense?
Yes. Yeah.
Because optics is only showing us the result of every iteration, not every function call, and it had to compute gradients and line searches for every single one of those iterations.
That makes sense. Okay, I'll stop the share now so we can move on to a different function.
Okay, great. Who wants to go next? Should I just call on you, or do you guys want to volunteer?
You can go. Let me share my screen. So I did the Himmelblaus function. So this is what the design space looks like. It's got 4 minimums. It's got a minimum of 0 in these 4 corners. So this is from -5 to 5 in both X and Y. And this is how it compares. Let me move this out of the way. So there's optics and SciPy. I start them both off at -5, -5, and then they hone in on one of the points, which is negative something like -3.8 and -3.3. Yeah.
Great. So they found that lower left optimum where there's really 4 different. So it completely depends on where you initialize this to which optimum it's going to find, right?
Yep. That sounds about right. I haven't tested that, but I would assume so.
So you started it in that basin of that
Mhm.
bottom left corner, and so it stayed in that basin. Yeah.
Mm-hmm.
Okay, great. How did the number of function calls compare?
So on the right is SciPy and on the left is optics. Optics does quite a few more. Oh. Let's see, that's about 240 and SciPy is about 82. So the ones for optics we should be pulling from the evaluations test file, right?
Yeah.
Okay.
So
Yeah.
that's for every single evaluation of the function. Yeah, if you
Yeah.
want to see that. Yeah.
Yeah.
Okay, great. And what's on the right?
Oh, that was a zoomed in. Let me pull it back up. That was a zoomed in thing because it gets really messy in here. So I was trying to see if I could make it a little bit cleaner, but it wasn't lending itself well to that.
Mhm. Okay.
Yeah.
Okay, great. Thanks, Ben.
Yep.
Let's see, Nolan, do you want to go?
Yeah. So I was pulling mine from the optimization text file, but right here I just have the data for the evaluations text. So I'm just finishing that.
Okay.
Okay, so on the left is optics. Let's see if I can zoom in a bit. On the left, so this was from the optimization text file, and this part is from the optics evaluations text file. And this on the right is the SciPy file. So it looks like SciPy goes all the way out here to test one of these points, and then comes back because they both end at the same point or close to the same point, you know. And I do have 3 of them plotted here. So if I just
Can you just crop the plot? So just set the limits on the plot to go from like -5 to +1 on the x-axis, and
yeah. Let's see.
I think, yeah, there you go.
Then -5 to
To 1 maybe.
1.
Yeah, and then on the y-axis, maybe -1 to +2 or something.
Oh, let's see.
There we go.
Yeah, okay.
Cool.
Yeah, so there is let's see. There. Okay, yeah, so all 3 of them are being shown.
Okay. Probably the points for optics are behind the calls for so the iterations.
Okay. Yeah,
So
yeah.
you'd have to rearrange the order that those are being plotted in order to see the actual iterations, but
Okay. Yeah. So yeah, okay, so they both follow, like, their function calls follow the same path in this one for the
yeah.
most.
Yeah. So click on the gray there. And then do you see up in the function definition there, it says equals series optics evaluation? See the very last number is a 3.
Mm-hmm.
Change that to a 1. Okay. Now do you see the blue points?
Yeah.
Okay. So that that last number is the order that it's being plotted. So you're now saying that gray is going to get plotted first. And
Okay.
then it just incremented up the other ones, you know, in the order that they were. So now they're both on top of gray. So you could actually click on the blue one and set that to 3 and say, yeah, I want that to be the third one. See, it's the second one. So now it'll bring it to the top.
Okay.
Um,
Yeah.
and
So then they're
yeah,
plotted
there
on
you
top
go.
of each other. Okay. Yeah. Yeah. So I'm still digesting what's happening here.
Okay, great.
Yeah.
Okay, let me share my screen. I'll show you guys what I worked through. So the function that I chose is this Rosenbrock function. This is a really fascinating one to me. And I initialized it. Let me just zoom in here a little bit so you can see. I initialized my solution to be just to the left up here. So I don't want it to walk downhill over here. I want it to be forced. You know, the gradient says that it should walk this way when really the minimum is over here. I just wanted to see what would happen. So I initialize it to, I think it's minus 0.5 and 3. Okay. And I did that for 3 different solvers. And I decided I don't have them labeled over here, but you can see that, let me just move this over so you can see what that looks like. Whoop, there we go. Okay, so you can see what this this design space looks like. And I initialize these to minus 0.5 and 3. So they all start right there. And then the orange one here is optics. So it walks as I would expect in this direction. It finds a minimum, you know, so it's walking in this direction. It's going to find a minimum in here and then hopefully start walking down this canyon, right? So so again, that's the orange stuff here. You can see it comes over here. It walks down this canyon, gets bounced back up over here and eventually settles into the real canyon and then iterates around to find the minimum. The gray is the BFGS method in SciPy.optimize. So anyway, you can see it walks way out of bounds here. And again, you know, I don't understand why it calls things so far out of bounds sometimes. Now I am just, there is a difference here. For the orange one, I'm just actually reporting the actual iterations, you know, so I don't know if we looked at the line search for the orange, you know, it would probably go well past all of these, right? So it would walk a ways out of bounds. And maybe that's what I'm seeing here on the BFGS stuff is that this is part of a line search. But it chose this point clear out here somehow, you know, I'm just not really clear on how it makes the decisions of the line search part of the algorithm. But anyway, you can see it converges. And then I tried another one called the Nelder-Mead. Now Nelder-Mead, there's actually a really nice Wikipedia page on Nelder-Mead. So if you just search for Nelder-Mead algorithm, you'll see this, and it's got some graphics over here that help you kind of understand what's going on. Basically, and you'll notice this is Himmelblaus function. This is the one that Ben just did. This is the Rosenbrock function that I'm looking at, and basically what it's doing is it's a simplex algorithm. And I'm not exactly sure how these work. To me, they seem like almost a form of genetic algorithm, although they're not exactly the same as what we would call a genetic algorithm, but they have kind of the same form. And it's also not gradient based. So it never computes the gradients, but what it's doing is it's always tracking 3 points and taking the minimum of those 3 points, at least in this 2-dimensional space. It's holding on to the minimum. Actually, I think the lower 2 of the 3, and then it's like flipping the 3rd point. And anyway, it's somehow using those 3 points to hone in on the optimum. And so what I wanted to see was, well, you know, in this example, they started over here, but I'm initializing my solution up here because I want it to walk down this canyon first and then around. I want to see how Nelder-Mead handled that. So this blue one are all of the calls that Nelder-Mead makes. And And so again, it initializes right here. You can see it makes a call above, but it actually doesn't walk this direction because it's not gradient based. It's almost more genetic algorithm based. It doesn't walk along the gradient, but it starts to walk along something that is downhill, but just not in the direct direction of the gradient there. And then eventually it hones in on this canyon and then wraps around and follows the canyon over here to the optimum. So anyway, just kind of interesting. Now, one of the fun things about what we've done so far is that we can see the design space, right? So we have a visualization of what this space looks like, where in most cases in optimization, we don't know what this design space looks like. And that's why we're doing the optimization, because we actually don't know, this is really a brute force method. In order to visualize this design space, we've had to compute it at every location in this space. And of course, once we've done that, then it's easy to find the optimum, right? This is a brute force method, but it allows us to visualize it. So in most cases, what you're dealing with are plots that look like this. You can see histories of where this thing has gone, but you don't actually know what the design space looks like around it unless you've somehow computed a slice through that domain. And that's one thing that I ask you guys to do quite often in your optimization is, well, let's take a slice, right? Let's see what this design space even looks like. And usually we're doing multi-dimensional or higher dimensional optimization. And so really we can only look at a 2-dimensional slice through this n-dimensional space, but it still gives you a sense of what types of things you're dealing with. Are there a whole bunch of local minima? Maybe a gradient-based optimization algorithm isn't going to work very well. If we have something like this, gradient-based optimization should work well for cases like this, where there's only a single global minimum and the contours are really well behaved. So anyway, so just knowing something about the design space is super helpful, but you don't always know something about the design space is what I'm trying to say. Okay, so yeah, go ahead.
So it's just like a terminology question within optimization, but when we say something is well behaved, does that mean it's kind of got that sphere function look to it? Or is that like a term in optimization?
That's a good question. So well behaved, what I'm meaning is that the gradients are continuous, the design space is continuous. A gradient-based optimization, basically if you poured water anywhere in here, then gradient-based is, the water is going to run downhill until it hits that minimum. This is a challenging design space, and this is not a well-behaved design space specifically for gradient-based optimization. Now there are other algorithms, and we're going to get into those next, that can handle things like this, but they're not gradient-based. You can't solve this problem by pouring water in there because there's all these little pockets where that water is going to end up. So it completely depends on where you initialize your solution. Yeah. What your initial guess is as to which pocket you're going to end in, and that does not guarantee that it's the global minimum.
Okay.
So that's one major drawback of gradient-based optimization methods, is that you cannot guarantee that it's a global minimum. Even if we take a slice and it looks like this in the design space, or even like this, we're only looking at 2 dimensions out of n dimensions. And maybe in these 2 dimensions, there is what appears to us to be a global minimum. But in the other dimensions, we may have a whole bunch of local minima. Or it could be that the range that we've chosen to the range of X and Y that we've chosen to even look at this design space, there is only one global minimum within that range. But if we were to expand this range, maybe there's another local minimum outside of this range. Does that make sense?
Mm-hmm.
If we had, for example, if we had really zoomed in and taken a range that was only this big on this plot, then we'd think, oh, this is a really well designed or a really well behaved design space. We only have one global minimum. Gradient-based optimization should work just fine. But that's not really true, right? If we expand our vision here a little bit, we see that there's a whole bunch of local minima. So
yeah. So in our writing, when we write about contour plots, we could say well behaved, but to be more explicit, we would say something like it's continuous and smooth or something like that.
Yeah, continuous appears to only have one global minimum, so gradient-based optimization methods should work well in this
Okay,
region or something. Yeah,
great. Thanks.
yeah. Okay, so that basically wraps it up for gradient-based optimization. I hope you guys feel a little bit more comfortable about what's actually going on in these algorithms and have some tools to be able to open up the hood a little bit, you know, and watch how they're walking around in the design space and understand why they're making those decisions, things like that. So again, some of the pros of optics are that it's you can parallelize it, you can see under the hood a little bit more easily. There's more information that's spit out about the optimization along the path so you can understand what's going on. And it has this ability to reset the Hessian every once in a while in order to ensure that it actually reaches the real optimum. But some of the benefits of going with the SciPy is that you have a whole bunch of options, right? There's a bunch of different optimization methods that you can choose from, and you can compare those, but it's harder to see under the hood. It just doesn't have as many tools set up to show you how it's making those decisions or what's going on. You'd really have to dig into the source code to do that. So the way around that is what we've done here, where we just print out every time this function is called, we just print it, and then we try to decide from those print calls what it was trying to do. So we can, for example, see when it's doing computing gradients or whatnot, or performing a line search just by trying to dissect, you know, the values that it's passing in here relative to the neighboring values, things like that. Okay, any questions on genetic algorithms, or excuse me, on gradient based before we move on to genetic algorithms?